All right, we're going to give this a go. I'm trying one of these videos at home today. Trying what Mr. Naughton said to do. Get up early in the morning and make a video. Okay, so it might be a little on the crazy side. The big topic we're going to be talking about tonight / this morning is going to be about 4.6a. And the topic specifically is about what do these graphs of tan and cotan end up looking like. Well, we've already talked about things like sine and cosine and their particular graphs that go with them. We know our sine graph, we know our cosine graph, and then we've seen their cousins, the inverted ones of cosecant and secant, where we took the individual graphs and then we drew in their asymptotes and then inverted them. Okay, now to finish off the cycle of the ones we need to take care of, we need to talk about these last two, tan and cotan, and what their graphs end up looking like. Now, the reason why we do these four first is because they basically are all relatable to each other. You can figure out what sine and cosine look like and how they shift and how they are modified. Getting to the cosecant and secant ones really means, do you understand how to do sine and cosine in the first place? Tan and cotan really sit off to the side of themselves. They are very different than the ones that we've seen in the past, and you're going to want to make sure that you catch as many pieces of this video as you possibly can. Now, there are a few good review questions that are up here in the top. I'm going to talk about them relatively quickly. Being able to find an amplitude period and a phase shift of a graph is pretty fundamental to this particular chapter. Amplitudes, as we all well know, are going to be placed out here in the front. This is an inverted cosine, so the amplitude is 2. The period is going to be really pulled down to that 2 pi divided by b concept, or 2 pi divided by 2. That's pi. And that was really fundamental in learning sine and cosine and secant and cosecant. It's going to slightly adjust a little bit when we talk about tan and cotan. And then if you did use the pull distributive method of pulling out the actual period adjuster, the interior piece right here turns out to be the phase shift. So the phase shift in this case are kind of like your C value, or H, if you want to think about that as pi. And that moved the graph over to pi before it actually got started. Okay, so you really should know how to get all those fundamental pieces. Some other things that are also out there too as well is making sure that you're really practicing your trig values when they come off of the unit circle. So for instance, like I'm thinking cosecant is really thinking about sine. Sine of pi over 4 would be root 2 over 2. And then we got that inverted value, and that's why it ends up where it is on the cosecant graph. That would be 2 root 2 over 2, or better yet, just root 2. Okay, and then we've got old stuff that we've seen back in 4.1 to 4.3. I think this is a 4.2 or 4.3 question based on, can you draw something in a specific quadrant? So I'm going to draw my triangle in the fourth quadrant with a 3 and 5 adjacent and hypotenuse, realizing that this is -4, and then going to thinking about, oh, that sine of x is equal to opposite over hypotenuse, or y over the hypotenuse, y over r, which would be -4 over 5. All right. So key fundamental kind of stuff. Don't forget about it. It is still extremely important. Now, to get into this tan and cotan concept, we really need to kind of take a look at what the graphs have as their fundamentals. And it does say to draw these two guys in 2 different colors. And it is good to recognize those 2 basic concepts. Now, the biggest fundamentals that you're going to see here for tan and cotan is probably to understand that there are times when tangent and cotangent are undefined concepts. Okay, and when they're undefined, they end up meaning that they have vertical asymptotes that are associated with them. In tangent, it has fundamental asymptotes at pi over 2 and at negative pi over 2 and pi over 2. It has ultimately 2 asymptotes that are normally drawn right here at negative pi over 2 and pi over 2. The other part that you're probably going to recognize in this is that it is not a relatively long wave. If it's going to get wedged between these two asymptotes, its period is going to actually change too as well. And this is something we've seen in the before when we were talking about the period of sine and cosine being 2 pi. The period of tangent and cotangent is pi. So it shortens up, and it ends up fitting into these individual asymptote walls. Now, what a tangent ends up looking like is that they are asymptotic, meaning that they don't have a range restriction like sine and cosine did. But what they do is they come up along the asymptote until they come up and cross at the x-axis right at the origin. So they have an arrow going down this way, and then they turn and go up the other asymptote going in the other direction. This is your basic tangent graph. Okay. Now it does have what we kind of can refer to as altitude concepts. The distance right here on the second and third critical points. So you've got critical points at the asymptote. You've got a critical point right here. You've got the critical point number 3, which is the 0. Then critical point number 4 is an amplitude point, and then you got critical point number 5, which is the other asymptote. So at these two particular values, you can talk about A values, about how tall the wave ends up being. But calling them an amplitude is kind of misleading, but they do end up having a stretching effect of what's going on. So when we look at these particular tan and cotan or tan graphs, we can say that the amplitude still has that same concept of A in the beginning. So I can call that 1. It still fits in the front. The period is going to be probably the biggest adjustment concept, and that is instead of using 2 pi over b, the formula has changed now to pi over b because its normal period is pi. And we'll end up in this case with pi divided by 1, which is just going to be pi. It doesn't have a b value inside there. No phase shift, no vertical shift yet. Domains are going to be slightly different. Let's talk about range first. It does go down and it does go up forever. So the range in this case would be from negative infinity to infinity. And the domain is every single asymptote that it'll possibly run into. Now you go to the very first one from the origin, and it'd be like x cannot equal pi over 2, but that's not the only place that it actually takes place. It'll happen again as the wave is made a second time. Here is the asymptote. I'll put that one in so it's pink. Stop, make it be pink. There we go. Now I'll make, it still didn't turn out to be pink. Oh well. And then the graph would come up like this and do it a second time. Okay. Now it's going to be every asymptote that occurs, and it occurs every pi amount in this case, or pi k, because you can write it as a recursive concept. The gap amounts that you're going to be using in between here is still the same concept that you've got 5 critical points, which ultimately means you need 4 individual gap values. So you still take the period and you still divide it by 4. In this case, it'll be pi over 4, and that's how much you have to move to get each individual critical point from an asymptote. Okay. Now, a negative tangent would only just make the actual graph turn over. So be thoughtful there that what we're going to do here is we're going to take this graph. Hold on, if I can get the thing to do colors for me. Maybe I just have to do a different color. All right, there we go. And it would just turn the graph over, and it'll flip the graph going in a downwards direction. Now, what I want you to really get in your brain is that tan in general is an upward kind of concept. You only want to think of it being flipped over if it has that actual negative on it. Now, the reason why I bring that up is because cotan is very relatable to tangent in the fact that it is just an out of phase tangent that has been flipped. Now, let me explain that. If I say something is an out of phase, that would just mean that ultimately it's going to have a different kind of asymptotes. Normally we would have asymptotes of negative pi over 2 and pi over 2, but now the asymptotes are going to be moved. They're going to be phase shifted. One's going to happen at 0 and the other one's going to happen at pi. Now, it still has a period going in between here of pi distance. So that's very similar to the same idea. And instead of it going in an upwards direction, cotangent turns it around and flips the idea, and it ends up going in a downwards direction. This is a cotan. Okay, it's been phase shifted over a pi over 2 amount. They're 90 degrees out of phase, but it's been flipped over at the same right. So you can kind of think that cotan is related to tan. It's just in that inverted sense. Okay, now if you ended up inverting a negative cotan, you would end up getting ultimately just a graph that, if I can get this thing to switch colors. Come on, switch colors. Oh, dude, it's being nasty to me. Okay, it would ultimately just be a graph that would come up and go the other way. So this would be a negative cotan, and this would be the original cotan. Okay, again, amplitudes work exactly the same. The period still works on that same formula of the period divided by b, or excuse me, the b value. Man, this pen is just not happy with me. I don't know what I made to make it mad. It'd be pi divided by b, and that would be, in this case, pi. The domain works exactly the same way, except that the very first asymptote is that it's at 0, and then it's plus pi k to move on to the next asymptote. Range, all real numbers are negative infinity to infinity n. The gap is still pi divided by 4. All right. So the big things to remember here, and the keys to making sure it works, is to remember that the period for tan and cotan is going to be the newest concept, and that is that it's going to be pi. The range is always negative infinity to infinity because they go up and down along the asymptotes. And the domain can be found by finding the first vertical asymptote and adding on to it the period n amount of times, whatever that period turns out to be, when n is an integer and so forth. Keep that in mind. Okay, now let's move this down just a little bit and see if we got some more information here. All right, now to finish off the rest of this particular worksheet that we've got here, remember that gap amounts are ultimately going to be found by taking the period and ultimately dividing that period value by, it does not like me today, the period divided by 4. And that part's going to be pretty consistent through all of them. Now, this amount should be added to the first vertical asymptote and to the center of the actual graph. Know the patterns, though. This is the big key to being good at these particular graphs. If I'm thinking tangent, it's a graph that goes up and through the origin. But if I'm thinking about cotan, that's a horrible graph, comes down and goes down like this and does not go through the origin. So you've got to keep a couple of things in mind. You've got 0 and pi are your two asymptotes in this case, and the one up above, you've got negative pi over 2 and pi over 2. So think about those when you're thinking about your ASYs and which graph you're basically talking about. So that's probably the key fundamental difference between those two individual graphs. Now, what we're going to do is we're going to get to how do we graph a couple of these things. And some of these don't really contain all the things that we really need to make sure we got all the good graph stuff. So I'm going to go right to this first one. First off, I'd for sure want to make sure I talked about an amplitude. The amplitude in this first one is 2. The period for a tangent, again, is going to be pi over b, which is going to be, in this case, pi, because there's no b value. Domain and range we'll come back to. No vertical shift. I'll put here none on this one because we'll do this one in red, hopefully. And the other one will be pi over 4. Now remember, we're graphing a tan. So having yourself a basic idea of what your expectation is that it's going to end up being a nice tangent wave that looks something like the following. The 2 is just going to end up pulling it a little bit. And the key part is to give yourself a good start on how you're going to get this guy going. And that's going to be to draw a couple of asymptotes, since it's a tan graph, between negative pi over 2 and pi over 2. The next would be to lock in the center of the tangent graph, because that piece is the part that's technically being phase shifted, and we don't have a phase shift in this case. And then we've got a couple of amplitude points that are going to be on either side, and those are going to be 2 up and 2 down. So I'm going to put 1 down here and 2 up, and I'm going to put 1 up there, and then I can come asymptotically up along the asymptote through the origin, through that other amplitude point, and ta-da, you got yourself a tan graph. Now keep in mind, these waves are continuous, so you can continue to make them. If I wanted to, I can make another tan graph over here. It'd still cross at that spot. It'd be 2 down and 2 up on the other side, and ultimately we would continue and make a brand new one that looks like that. Okay, now again, domain and range. The domain would be from x's that are not equal to pi over 2 plus pi k, because it happens every pi that you get another asymptote, and the range is negative infinity to infinity. Now I hope I can change the colors here. Let's see if I can. Okay, let's see if that did it. Yeah, we got purple. Now, what if I was going to go to that same graph, but I was going to actually install a +2 concept? Now, the only thing a +2 concept would do to it would be take the whole entire tan graph and it would shift it up. And ultimately, it would make a brand new midline that would go inside here, just like you've done when you did sine or cosine. Sorry, that's not the greatest. Okay, and it would take every one of these points and it would just shift them up 2 points. So this would end up being up here at 4, and this one would end up, instead of being 2 down, it'd be on the actual x-axis, and this graph would come up and it would go out the asymptotes. And ultimately, you get the same exact graph. You just ended up grabbing the whole graph and moving it up. Okay. All right. Now let's move into a little bit more thoughtful kind of graph. Now, in example number 4, before I ever touch going onto a graph, I think it's really important to give yourself some credit that you have important information over here that you need to take care of beforehand. First off, I always like to think about the cotan, or whatever graph you're talking about, whatever function it needs to be, to give yourself a sketch of what you're thinking about. A negative cotan would ultimately look very much like a tangent graph. So instead of it coming down, it would end up being flipped, and it'll look a lot like a tangent, and normally would be stuck between 0 and pi. All right, so let's keep that in mind, that our graph should end up looking like that. The amplitude, not listed here, is 1, so I think that's pretty standard. The period is going to be pi divided by b, which is still going to be pi in this case because we don't have a b value. The domain and range we'll come back to, but ultimately the phase shift is going to be positive pi. Now, this phase shift value would normally mean that we take the 0 that we've got right there, and we would take the 0 and move it the complete value over. Now, in a normal inverted cotan, it would be between 0 and pi is where we would be at, and this particular value would be where we would cross the x-axis. So we would want to take that whole entire point and move it 1 full pi distance away, and this is where the graph is really supposed to be at. The asymptotes would be pushed over the same amount too as well. So everything that we would normally draw is now going to be drawn a pi distance pushed over. And I like to move the central 0, because ultimately moving the asymptotes can be adjusted to by a period adjuster, and you got to be careful. I think this guy locks in much easier and you can get it. The gap is still going to be pi divided by 4. So I can go over and down 1 and up 1, and I've got my inverse cotan that has been phase shifted. Now, the funny thing about this one is that it was phase shifted an entire pi amount. And since the period is only pi amount in this particular one, it's like you really phase shifted it right on top of its continuance, because over here in the past, it would have had the same exact inverted cotan, and we would end up having the same graph as we did before. So if you end up phase shifting any of these graphs, the amount of their period, you end up with the same graph all over again. All right. Domain and range, again, domains are going to be where it's not equal to. And you could ultimately say that the first one that you really should have run into is pi, and it's going to be a pi amount each time. So it's really at pi k where it doesn't exist, and negative infinity to infinity when it comes to its range. Now, a funny piece about tan and cotan is this question that's actually listed down here below. It says, what's another equation for that particular graph? Now, if you look at it, you're probably like, oh, it's a tangent graph, but they started it out as a cotan. So you could really think about this graph that's listed here as a y equals tan graph with a amplitude of 1. So it's like tan. But the problem is the tan would normally be between negative pi over 2 and pi over 2. So it's technically been phase shifted in a positive direction, or x plus pi over 2. Not plus, excuse me, it would be minus because it's been pushed to the right. And you got to watch out for that because it's a really easy mistake to make, just like I did right there. So it's kind of hard to tell. What are you really talking about? Is that an inverted cotan or is it really a tan? Now, the really answer to that is that both answers are technically right. I try to always write the graph that has the least amount of phase shift. That's the one I per se say is the most correct version of it. Okay, now let's try one that's actually got a phase shift. Example number 5. Tan. All right, we've got an amplitude of 1. I'm going to make myself a little sketch. It is a tan graph, so it should look something like this, except it's going to be pushed over. The period is still 1, so we're still looking at pi for the actual period. Domain range we'll come back to, and the phase shift is a negative pi over 4. Gap, pi over 4 as well too. Now, again, a normal tangent graph would cross at the x-axis. So this negative pi over 4 is actually lifting up the 0 and it's shifting it over here. Now that's going to shift all of the asymptotes at exactly the same time. So the asymptotes are not going to be at pi over 2 and negative pi over 2, but the ones that are at pi over 2 have been shifted over to pi over 4, and the one that was at negative pi over 2 is going to be shifted to negative 3 pi over 4. And it's still a distance between here of pi. Now, amplitudes are 1, and ultimately you got yourself a nice little tan graph. That's what it should look like in the long run. Domain and range. First domain or first asymptote that you came across was pi over 4, and that actually happens every pi k as well too, so can't equal those, and negative infinity to infinity when it comes to the range. Okay, all right, still same kind of idea. Keep reiterating what you got right there. Now pushing it down to example number 6, the last one that's in this particular deal. They threw a whole bunch of stuff at us. Let's see if we can try and pick it off. Amplitude of 2, an inverted cotan, but it's been phase shifted. Oh man, we'll have to deal with the phase shift, but I'm thinking an inverted cotan would kind of look like a tangent graph. Oh man, that's going to be funny. Let's try and figure out what we got here. Period is no b value, so we're still talking pi. Phase shift, since that b value has been pulled out, is a positive pi over 2. The gap is pi divided by 4. The vertical shift is negative 1. Now, you got a lot of things going on right here. First off, I would suggest that you push the actual phase shift over pi over 2. So normally a cotan would be between 0 and pi, and it would cross right here. So if it had been pushed a pi over 2 amount, this is where it would end up. All of the actual asymptotes will be pushed that way too as well. So we'll get an asymptote here at pi over 2 and another one that's over there. Now I might have to make one that's on this side and draw the graph in that spot. I'll start by graphing it over here. It's not going to cross at the spot right there. Let's see if we can erase that. I'm going to erase it because ultimately it has a vertical shift that's pushed it up 1. Oh my gosh, so many things. Amplitude of 2, so it pushed this point down to here. and you'd get a graph on the other side that's pushed up 1, 2, somewhere up there. So this is what the cotan would look like on this side. Oh man, that's not the best one. With a midline right here. Let's go and put that. Oh man, I messed it all up. Because the midline's not at 1. The midline's at, oh man, gee, you got to get that fixed. Midline is at -1. Jeez Louise, let's put that guy in there first so we don't mess it up anymore. Phase shift, this is where the coordinate will be pushed down to, down there, pushed up to, right up there, and this is what the cotan would look like, the inverse cotan. Now that's not really the best graph because it's kind of going off. We should be able to recreate it over on the other side, and that would mean that it's crossing at the midline right here, 2 down, 2 up, and we've got our inverted cotan that's asymptotic like that. Okay, domain, x's that are not equal to pi over 2 plus pi k, because we've got that same distance, and the range -infinity to infinity like always. All right, the only way to get good at these is practice, guys. Got to keep practicing. And most importantly, of all the end stuff that we've been doing here, know the patterns. Know the patterns that you're basically talking about and the normal asymptotes of where they are drawn, and you can go from there.